Welcome back to the last episode in the IB Physics topic B section. Today we'll be looking at circuits. So let's just dive right in. So in circuits, there are going to be some symbols. You don't have to memorize them, but these are just like sort of symbols that you might see, and it's good to know what they are. So for example, this right here is a cell. Two cells connected together is a battery. This just means an open switch. This means a closed switch. This is a filament bulb, so that's just a lamp. This is a resistor. This is a variable resistor, meaning the resistance can change. This is a voltmeter, so it measures voltage. This is an ammeter. This is a fuse, you don't really need to know that. This is a diode, also don't need to know that. This is a light emitting diode, which is a bulb, but I don't think you need to know that. And this is a light dependent resistor, and this is a thermistor, so these just means the resistance changes based off of the temperature and the light. So yeah, that's pretty much it. You don't need to memorize these, like I said. It's just good to have an idea of what the symbols are. So now let's look at charge and current. So charge has the symbol Q, and it's basically just an electron or a proton or a multiple of these. So it's just a plus or a minus. And the unit of charge is coulombs. So if I have a charge of positive 5, that means I have 5 protons, basically. And basically, when we look at current, we just see it as a rate of flow of charge. So that means change in charge by change in time, or if it's at a very particular point, we can just say it's charge by time. And charge by time has units coulombs per second, or more simplified, amperes. And because they're called amperes, we measure them with an ammeter. And this right here is an ammeter, so if you do your IA on this topic, you might have to use one of these. Next, we'll look at voltage. So voltage is also called a potential difference, and it has the formula work per unit charge. And the unit of it is volts. The symbol is V, and it's measured by a voltmeter that you see on the right. Next, we'll look at resistance. So resistance is the voltage divided by the current. So it has units volts per ampere, but we can call that as ohms. And resistance is R here. So R is V over I. And resistance is also proportional to the temperature, which is something we'll look at very soon. If you do electrical engineering or something like that in the future, you'll see these. These are resistors, and that's how they look in real life. So now let's look at resistivity. So resistivity is basically how much a material wants to resist based off its inherent properties. The symbol is like this curved P here. It's also here. And the units are basically ohm times meter, and that's called ohm meters. And the equation for resistivity is AR by L, where A is cross-sectional area. So here it's the area of this circle. R is the resistance of this wire. And L is the length of the wire. And let's look at Ohm's law now. So Ohm's law basically says that V equals IR. If this looks familiar, it's because it's just a rearrangement of this equation here, R equals V over I. And it shows us that the current and the voltage here are basically linearly proportional. So here, for instance, our gradient would be current divided by voltage. And if we were to rearrange this equation, we'd see that the gradient here is actually 1 over R. So the gradient here is 1 over the resistance. And because this is a straight line, we call it an ohmic resistor. This is not a straight line, so that means it doesn't follow this relationship here, so it's just called a non-ohmic resistor. Now we'll look at series and parallel connections. Series just means that all the resistors are connected in a straight line. So here, this, and this is just one straight line. There's nowhere for the current to bridge, right? So whatever current starts here ends back here by going through the exact same loop. So in this sort of sequence, the total resistance is the sum of these three resistors. So the resistance here is 3 kilo ohms plus 10 kilo ohms plus 5 kilo ohms, which is 18 kilo ohms. If we wanted to calculate the current flowing through, we just use V equals IR now. So we have V is 9 and we have 18 kilo ohms. So 9 divided by 18 kilo ohms is the same as 9 divided by 18,000 ohms, and that would be our current. So it's a very small current running through this circuit. Now, this is a parallel connection, and that just means that the current bridges off. So at this point here, some current goes to the right, but some current goes forward. Again here, some current goes to the right, some current goes forward, and here, the remaining current that went forward goes to the right. So that's why it's called parallel, because the current splits. And in parallel, we can't just add them all together directly. Instead, it follows this formula here. So 1 over resistance is 1 over R1 plus 1 over R2 plus 1 over R3. So in this case, 1 over a resistance would be 1 by 10 plus 1 by 2 plus 1. And that would be, and then we'd have to like invert that, so raise that to the power of -1 to get our R. And yeah, that's pretty much it for series and parallel connections. Just one thing to notice is that the current usually follows the path of least resistance in parallel connections. So that means that when we're going like this, a lot more of the current will follow the straight line than it will go down here, because this has a 10 kilo ohms and here is a little bit of a lower resistance. Okay, so now let's look at power. So power is has two definitions, or three definitions if we're being precise, in electricity. It means the exact same thing as it does in mechanics, it's just energy per unit time, but there's three different ways we can formulate that. I've written this one here separately because it's a bit misleading. So we'll look at these two definitions first. So this is dissipated power. If something in an exam says dissipated, you instantly know that you should probably use this one right here. And it just says that power is I squared R. That means that power is the current square times the resistance. And that's the exact same if we use Ohm's law as a V squared by R, which means that it's the voltage square divided by the resistance. So these are two definitions for power. So from these definitions, we can see that power is a quadratic function. So if we plot power with voltage, for instance, it's a quadratic function right here, and it's not defined at 0. Sorry, just ignore that. So that's going a little bit deeper beyond the IB syllabus. So basically, yeah, it's a quadratic function, as you can see right here. And I square R would be very similar. So it would also be a quadratic function. But if we look at power as IV, that would now be a very misleading thing. Because looking at this, we're going to think, oh, power is a straight line with current and a straight line with voltage. But if we look at this graph, we see it's not true. So yes, this relation is correct, but I would be very hesitant to use it because it's quite a misleading relation. So yeah, just be careful when using this formula. Don't assume that it's linearly proportional, because it's not. Lastly, we just have to look at internal resistance. Internal resistance is basically this small r here, and it means how much a battery resists. So no battery is perfect, so that means, say, this battery here is 9 volts, but some of it is lost because there's a resistance inside the battery. So this symbol right here is called the EMF, electromotive force. It's the same as voltage for all practical purposes. And basically this equation says that EMF is I times R plus R, where this big R is the external resistance and this small r is the internal resistance. So this is just V equals IR, but expressed as a sum of the internal and the external resistance. One thing to note here is that if it asks you for terminal voltage, which basically is this E right here, minus I times small r, the voltage available in the circuit, that is literally just V equals IR. Because right now, V is the same as E here, and IR plus I small r is what we have now. So if we just subtract I small r, we get I big R on the left, which means that V is just E minus I small r. So this is pretty much the entire of B.5 covered. I'd suggest you know this topic quite well for the exam because it is one of the more important topics. If you do have any questions, please let me know in the comments down below, and I hope it helped you. So thank you so much for watching.